In this video, we are going to introduce the concept of a partial order on a finite set. And so, in lower level courses, we're used to orderings on sets, the total order on the natural numbers, which we're able to extend to the real numbers. Given any two real numbers, there's a way to compare them. One must always be bigger than the other. But of course, if you've ever taken complex variables, you know this idea ends when you include square root of -1. There isn't a well-defined way to compare things as a total order. In general, it turns out the best you can do is what's called a partial order. And it's also clear that this idea of total order is kind of strange when you start talking about subsets. So which should be bigger, the subset containing 1 or the subset containing 2 and 3, for instance? So the problem is, in general, you don't always have a well-defined total order on a collection. The best you can do is what we're going to call a partial order. So recall, given a fixed set X, a relation is a subset of ordered pairs. And we often write A, R, B, A is related to B, for ordered pairs in the relation as a change in notation. And the most common type of relation studied in proof writing courses is the equivalence relation. So an equivalence relation is a relation that is reflexive, symmetric, and transitive. That means everything is related to itself. If I am related to you, then you are related to me. That's what it means to be symmetric. And transitive says if X is related to Y and Y is related to Z, then X was related to Z. And the most common equivalence relation we work with in mathematics is the equal sign. Well, the definition of a partial order is almost the same. So a partial order, and the sign we actually usually use is less than or equal. So a partial order written less than or equals, a relation like this is called a partial order if it's reflexive, reflexive and transitive, but the other condition, we replace symmetry with anti-symmetry. And anti-symmetry says if X is at most Y and Y is at most X, then in fact X is equal to Y. So the way you're supposed to be thinking of is that you're comparing things and some are better than others. Everything is at least as good as itself. If X is worse than Y and Y is worse than Z, then X is worse than Z. So you have some sort of comparisons that are transitive. And moreover, if two things are as good as each other, they must be in fact the same thing. And so why this is called anti-symmetry is because the only symmetric pairs are those that you're required to have because of the reflexive condition. And as you can guess, we define X is less than Y, means that X is less than or equal to Y, but they're not the same point. And so the point is, if you restrict your attention to this relation, the strictly less than relation, it is irreflexive. Nothing is strictly less than itself. And it has no symmetric pairs at all. If X is strictly less than Y, then Y cannot be strictly less than X. But it is in fact transitive. However, for proof purposes, for some strange reasons, it's become more traditional to use the less than or equals to sign. But you often see this notation as well. And so this is the notion of a partial order. And of course, one of the questions is, why do we use the word partial order? Well, because as we'll see in some examples, it's perfectly fine to have two elements, X and Y, such that X is not less than or equal to Y, and Y is not less than or equal to X. This sometimes happens. So the first example is the natural numbers under the usual ordering we teach in grade school. It's clearly transitive and reflexive. X is less than or equal to X for all X. And it's certainly anti-symmetric. The only way for X to be less than or equal to Y and Y to be less than or equal to X is for them to be the same number. This is actually not the only partial order we often study. in the proofreading courses, you've actually also seen example 2 or 3, even if they didn't call it that way. So the collection of subsets of X forms a partial order under the inclusion operation. Every set is a subset of itself, for instance. And if A is contained in B and B is contained in A, then A is equal to B. In fact, sometimes you say that this is the definition of equality for sets, although it's usually a proposition you prove. And we're all familiar with this if you've taken the proofreading course recently. Whenever you want to show an equality of sets, the proof breaks up into 2 parts, containment one way and containment the other. And this boils down to the fact that this is a partial order, in particular is antisymmetric. And so the antisymmetry gives you the fact that once you've proven these 2 facts, you get the conclusion you wanted. On the other hand, it's usually a homework exercise to show that if A is a subset of B and B is a subset of C, then A is a subset of C. What's the usual proof? Take an X in A. Because A is a subset of B, by definition of subset, X is an element of B. Because B is a subset of C, X, by definition of subset, X is an element of C. Therefore, every point in A is also a point in C. And so, again, the reason why it's called a partial order is because you can see that the set containing 1 is in fact a subset of 1, 2. So you do have an ordering here, but it's only partial because 1 is not a subset of 2. The set containing 1 is not a subset of the set containing 2 and 3, or vice versa. So we can't compare these two. There's no comparison under a partial order. And that's one of the hallmarks of Poset theory, or the theory of partial orders, is that it's partially ordered because sometimes you can't compare 2 things. And when 2 things can't be compared, they call this incomparable. So I'll put that word on the next slide, actually. As one last example, the set of natural numbers is also partial order under the divisibility relation. That is, we say A is less than or equal to B if and only if A divides B. In case you need a reminder, A dividing B means that B is equal to Q times A for some integer Q. That's the definition we usually teach for the division relation. And certainly you see that this relation must be reflexive because A divides A, because A can be written as 1 times A. Now let's look at this should be antisymmetry. Suppose A divides B and B divides A. Then because A divides B, B can be written as Q times A for some integer Q. Because B divides A should be able to be written as Q prime times B for some other integer Q prime, not necessarily the same one. Well then, doing substitution into this first equation, we see B is equal to Q times Q prime times B. Since multiplication is associative, we can move the parentheses over. And so we have B is equal to Q times Q prime times B. We're working over a integral domain, or, well, at least if you work with integers or rational numbers, you can cancel out the b on both sides and you have 1 equals q times q prime. Because q and q prime have to be integers, it tells you q has to be plus or minus 1. And because these are positive integers, it tells you q has to be 1. But that means b is equal to a. And so we get antisymmetry. Finally, we have to show transitivity. Suppose A divides B and B divides C. Then since A divides B, B should be expressed as Q times A for some integer Q. Because B divides C, C can be written as Q prime times B for some integer Q prime. Again, doing a substitution for QA into B, we get C is equal to Q prime times QA, but by associativity you can move the parentheses over, and you now see that C is an integer, some integer times A. Therefore, A divides C. And so those are two of the most common partial orders we see, and they pop up repeatedly in the coming lectures as well. A final example I won't spend much time on comes from group theory, or even ring theory. The subgroups of a group form a partial order under inclusion. In fact, they call this the subgroup lattice. We won't talk about lattices much in this course, but a lattice is a partial order that has extra structure. Namely, it has something that generalizes the notion of intersection and union from the case of power sets. Only in more generality, we call this meet and join, and it satisfies certain axioms. And a lot of partial ordered sets are actually lattices, and they're very nice to work with. But for our purposes, we're only going to focus on general posets. Finally, some notation. We're going to write P, this is a curly angle Q, and say Q covers P whenever P is less than or equal to Q. This is all occurring, by the way, in some partial order. So given any partial order, and any two elements, little p and little q, we're going to say Q covers P if P is less than or equal to Q. P is not equal to Q. And for any other element R, if R is between P and Q, then either R is P or R is Q. In other words, somehow Q is greater than P, but there's nobody in between. Another terminology that I haven't mentioned yet is P and Q are incomparable. If P is not less than or equal to Q and Q is not less than or equal to P. It should be clear from context what we mean when we say not less than or equal to. We mean it is not the case. So as a logic statement, it is not the case that P is less than or equal to Q. And it's not the case that Q is less than or equal to P. And so we already saw in the subset poset that there do in fact exist incomparable pairs. Also, the last bit of terminology I haven't used yet. What does the word poset mean? A poset is nothing more than a set that has a given partial order on it. So the po is supposed to be standing for PO, for partial order, partially ordered. So partially ordered set is a poset. Finally, to conclude this horrible lecture just on terminology, oftentimes we will use pictures to denote our posets, and we call these pictures the Hasa diagram. And what you do is you list the elements of your poset, and you have your cover relations. So 1 is greater than or equal to the empty set. This set is greater than or equal to the empty set, and there's no set in between. And so I draw this directed arrow. And similarly, this set's contained in that set, but there's nothing in between, so I draw this directed arrow. And so the directed arrows correspond to pairs where Q covers P. And so how do you determine whether or not two elements in this poset are comparable or not? Well, you're just looking whether or not there's a directed path. So for instance, since there's a directed path from here to here, it tells us that this is a subset of that. Although you can verify that directly, but for arbitrary posets, it's how you determine from the Hasa diagram which two elements are comparable. So whenever you see square bracket n, I'm thinking of the integers 1 through n with the usual ordering. By the way, they call this the total order when there are no incomparable pairs. And so this is the Hasa diagram in this case. Finally, here's the Hasa diagram for D sub 60. This is not a dihedral group. This is the divisors of 60. Partially ordered by the divisibility relation. So the divisors of 60 are 1, 2, 3, 5, 4, 6, 10, 15, 12, 20, 30, and 60. And here they're partially ordered by divisibility. And so you see because 3 divides 6, we have the edge here. All the direction, gravity always moves down, so 6 is covering 3. And that's because there's no integer in between them. that's divisible by 3 and divides 6. Similar here, there's no integer that 15 divides that also divides 30, and so these are cover relations. And for instance, let's see here, 2 is less than or equal to 30 because 2 divides 30, and here you see exactly one example of a path. And so for right now, that concludes this video on partially ordered sets. It's most of these videos are going to be a lot of terminology and drawing pictures and looking at examples, but eventually we'll get back to counting problems.